Assalamualaikum everyone. So today we present you our slide which is the title is Molecular Orbital Theory. This is our group member. We have Dana Shahmina, Sharifa Arina Sofia, Nur Nasoha and Nurul Arifah.
Next, let me briefly go through the agenda for today's presentation. First, we will start with the objective where we explain the purpose of presentation. Then, we will move on the introduction of molecular orbital theory. After that, the findings and discussion section will cover the main concept and explanation in detail. Next, we will conclude the presentation by summarizing the key points. Finally, we will end with the reference used throughout this presentation. This agenda will help guide us step by step through the topic. These are the main objectives for today's presentation. Basically, by the end of this session, you should understand how molecular orbitals are formed, how bonding and antibonding orbitals are different, and how this theory helps explain covalent bonding. We also look at why some molecules are magnetic while others are not. And finally, we will learn how to identify HOMO and LUMO, which are important for understanding chemical reactivity.
My name is Sharifa Irina Sofia binti Said Anwar Bahar, and I would like to share to you guys about molecular orbital theory. So, molecular orbital theory is when atomic orbitals interact to form molecular orbitals, covalent bonds are created. Furthermore, it also explains how chemical bonding causes the oxygen molecule to be paramagnetic. For almost every covalent molecule that exists, we can now draw the Lewis structure, predict the electron pair geometry, predict the molecular geometry, and come close to predicting bond angles. However, one of the most important molecules we know, which is the oxygen molecule, presents a problem with respect to its Lewis structure. As you can see in the slide, I've attached a Lewis structure of the oxygen molecules. This electronic structure adheres to all the rules governing Lewis theory. There is an O double bond O, and each oxygen atom has 8 electrons around it. However, this picture is at odds with the magnetic behavior of oxygen. By itself, oxygen is not magnetic, but it is attracted to magnetic fields. Thus, when we pour liquid oxygen past a strong magnet, it collects between the poles of the magnet and defies gravity. Such attraction to a magnetic field is called paramagnetism. Molecular orbital theory also states that the overlap of two similar orbitals will produce bonding molecular orbitals and antibonding molecular orbitals. In molecular orbital theory, we also can determine the magnetism of a molecule, whether they are dimagnetism or paramagnetism. Other than that, HOMO and LUMO also can be determined by molecular orbital theory. Highest occupied molecular orbital, HOMO, and lowest unoccupied molecular orbital, LUMO, are fundamental concepts in molecular orbital theory. HOMO and LUMO are called the frontal molecular orbitals because they define the boundary between occupied and unoccupied electron states in a molecule and play a critical role in determining its chemical reactivity. These orbitals play a crucial role in determining the optical and electronic properties of molecules, such as their ability to absorb light, undergo chemical reactions, and conduct electricity. These are the examples of the dimagnetism and paramagnetism. As you can see on the left, the liquid nitrogen is poured between the two magnets. There is no attraction between the two magnets as liquid nitrogen is dimagnetism. However, on the right side, liquid oxygen is poured between two magnets, and as you can see, there is an attraction between the two magnets as the liquid oxygen is paramagnetism.
Now I'm going to explain about the discussion part, which is the interactions of the atomic orbital. That we have two types, which is bonding molecular orbital and antibonding molecular orbital. So bonding molecular orbital is formed by constructive interference, or we call it as additions of wave. So constructive interference increase in amplitude is analogous to the buildup of electron density between two nuclei. Bonding molecular orbital have a lower energy and a greater stability, and electron density is the highest between the nuclei. So for the antibonding molecular orbital is formed by destructive interference, or we call it as subtraction of wave. So destructive interference is decrease in amplitude, is analogous to the decrease in the electron density between two nuclei. Antibody molecular orbital have a higher energy and less stability, and contain a node where the probability of finding an electron is 0. Okay, the next one is the magnetism. So we have two types of magnetism. The first one is dimagnetic, and the second one is paramagnetic. So the diamagnetic, we have electron configuration that in all electrons are paired and no net magnetic moment, and the behavior is weakly repelled by an external magnetic field inducing an opposite field, and the magnetization is temporary and no residual magnetism, and the temperature is independent of temperature. And the examples of the dimagnetic is gold and also the helium. Okay, the next one is the paramagnetic. The electron configuration is contain one or more unpaired electron. The behavior is weakly attracted to an external magnetic field, and the induced field forms internal magnetic field aligned with the applied field. And the temperature is awakened as the temperature increases because of its thermal energy randomizes spin. And the example is sodium and also aluminium. How to determine the magnetism is, the first one is check electron configurations by write out electron configuration and draw orbital diagram by using the Hans rules. And the second one is by looking unpaired electron. If any orbital has a single electron, is paramagnetic. If all pairs, it means that dimagnetic. So the last part of discussion is HOMO and LUMO. So what is HOMO and what is LUMO? HOMO is the highest occupied molecular orbital. Electrons from HOMO are donated, a specific molecular orbital fully occupied by electrons, and it is the highest energy molecular orbital from which an electron can be assigned to higher energy level like the LUMO. The energy of the HOMO is important for the molecule's ability to donate electron, and the characteristic for HOMO is null nucleophilic content. Okay, for the LUMO, LUMO is the lowest unoccupied molecular orbital. LUMO is receive electrons, and the lowest energy orbital that is not occupied by electron, and it is the frontier molecule orbital that capable of accepting an electron from the HOMO or another electron donor. And the energy of the LUMO determines the molecule ability to accept electrons. And the characteristic of LUMO is the electrophilic content.
Assalamualaikum, my name is Nur Nasuha binti MD Ramzi, and today I will give you the conclusion of our presentation. So, molecular orbital theory (MOT) changed the way we understand chemical bonding. It used ideas from quantum mechanics to explain how atoms join together and why molecules behave the way they do. Instead of seeing bonds as simple connections, MOT shows that atomic orbitals combine to form new orbitals. Some make molecules more stable, while others make them less stable. This theory helps explain things like magnetism, how molecules work, and why the arrangement of electrons is important. MOT is also useful in real life, from designing new medicines to developing better materials. In short, it helps scientists understand why atoms bond and how to use that knowledge in science and technology.